In this segment, we're going to talk about the vapor compression refrigeration cycle or heat pump cycle. So just kind of give you a roadmap of where we've been and where we're going. We've already talked about power cycles, talked about gas power cycles. So that was the Otto, the diesel, the Brayton, and we talked about different things that we could do with the Brayton cycle to increase the thermal efficiency. Then we talked about vapor power cycles. That was your Rankine cycle. And we talked about different modifications that you could do with the Rankine cycle to increase the thermal efficiency. Now we're going to shift away from the power cycles and we're going to go to the refrigeration and the heat pump cycles. And if you need a review, a more in-depth review on refrigeration and heat pump cycles, there is a review video in the Thermal 1 review videos. But we're going to go through a really quick review right now. So a refrigeration cycle is a cycle that pulls heat out of a low temperature reservoir and dumps it into a high temperature reservoir. Low temperature reservoir is your refrigerated space. The high temperature reservoir is your kitchen, and you have to add some amount of work to your cycle in order to accomplish this. Sometimes you have a work output, sometimes you don't. A lot of times you don't. For most of the cycles, for most of the refrigeration and heat pump cycles, you don't have a work output. But we'll talk about that when we get there. Now in Thermal 1, we were content just to say, okay, well, we'll treat this cycle as a black box, and we don't really care about what's going on within that black box, and that's not really the case anymore. So we're going to analyze what's actually going on in that box. But before we get there, the coefficient of performance for a refrigeration cycle, you could also call that beta instead of just COP with a subscript R. This is equal to what you're interested in over what you have to put into it. So what I'm interested in is I'm interested in pulling heat out of that refrigerated space and into the cycle. So that's my QN. And what I have to put into it is my work net in. And of course, if you don't have a work output, which your refrigerator probably does not produce any work for you, if your refrigeration cycle doesn't have a work output, then your work net in would just be work in. You could also note that for any thermodynamic cycle, the work net in is equal to the Q net out. And so you could put your coefficient of performance in terms of just Q in and Q out. It's not a percentage, unlike the thermal efficiency for a power cycle. The coefficient of performance will be just a number. And whether or not it's a good number or a bad number depends on the temperature of those two reservoirs that the cycle is operating in between. And if you want to look more about that, you can review the video on second law limits on cycles. There's a video in the Thermodynamics 1 review section. And then one last term is the refrigeration capacity. So this is the rate at which heat is being removed from that refrigerated space, and it's commonly expressed in tons of refrigeration. And there's a couple of conversion factors on your conversion factor sheet for that unit. A heat pump cycle, if you look at the cycle itself, like where the arrows are going, it's the exact same as a refrigeration cycle. The only difference for a heat pump is what we're interested in obtaining. So with a heat pump cycle, we're interested in heating, say, our high temperature reservoir, which might be our house. So we're interested in the Q out of the cycle and into that high temperature reservoir. Unlike a refrigeration cycle where we're interested in the heat that we're pulling out of that low temperature reservoir, the Q into our cycle. I can express a coefficient of performance for a heat pump. I sometimes write that as gamma. That's what your book uses. I kind of go between both of those terms. But it's what you're interested in over what you have to put into it. And what I'm interested in is heating my house. So that's my Q out. And what I have to put into it is work net in. If your work out is 0 for this particular cycle, then your work net in is just work in. And of course, you can put that in terms of just Q outs and Q ins if you'd like to. And just like the coefficient of performance for a refrigeration cycle, the coefficient of performance for a heat pump cycle is just a number. It's not a percentage like the thermal efficiency for a power cycle. And once again, if you want to know the limits of that, if you want to know whether a coefficient is a good one or a bad one, make sure you review the Thermal 1 video on the second law limits on cycle performance. And then lastly, the heating capacity is the rate at which you're adding heat to that high temperature reservoir. So it's Q dot H or Q dot out of your cycle and into that high temperature reservoir. All right, so we can talk about refrigeration or gas pump heat pump cycles where the working fluid stays in a gas phase, and that's our reversed Brayton cycle. And that particular cycle is the one where you have a work output associated with it. You can also talk about vapor refrigeration or heat pump cycles, and that would be a vapor compression refrigeration cycle. That's the one that we're going to talk about now, where your working fluid is some refrigerant like R22 or ammonia or something like that, not water. All right, so let's look at this on a TS diagram. And I'm going to be talking in terms of a refrigeration cycle, but the actual cycle for a vapor compression heat pump cycle is the exact same thing. You're just interested in something that's different, interested in the Q dot out of the cycle as opposed to the Q dot in. All right, so from state 1 to state 2, you undergo an ideally isentropic compression within a compressor. And I've drawn a sort of reciprocating compressor design, but your book draws the compressor slightly differently. It's okay. It's just a compressor, and in this class, we analyze all compressors, regardless of the design, the same way. So from state 1 to state 2, ideally isentropic compression within that compressor. Then from 2 to 3, you go through a constant pressure heat rejection process. So P2 and P3 are the same. And since we're going through a phase change from a gas to a liquid, we call this type of heat exchanger a condenser. And it's coming out as a liquid, and unless it's otherwise specified, you can go ahead and assume things are coming out as a saturated liquid if you need to. Then from 3 to 4, you have an isenthalpic expansion in a throttling process or a throttling valve. So H3 and H4 are equal to one another. And you'll notice from 3 to 4, it's drawn as a dotted line, and that's because it's an irreversible process. Ideal cycle assumptions still apply. So all of these processes, if it's an ideal cycle, all of these processes would be reversible. Except for that throttling process, which is inherently irreversible. Then from 4 to 1, you go through a constant pressure heat addition process. That would be from the refrigerated space, and you're coming out as a gas, so that would be state 1. And yeah, I guess that's all that we really need to know. So let's kind of walk through this cycle and see what it looks like for the refrigerator that's sitting in your kitchen. So the refrigerated space is the low temperature reservoir. The kitchen is your high temperature reservoir. And what we're going to do is, in a second, we're going to look at the video on the left-hand side, and we're going to look at the path of the refrigerant as it flows through that loop. So it's starting out in the refrigerated space. So it's starting out on this video from state 4 to 1. It's passing through the low temperature reservoir, and it's going through the evaporator. All right, so it starts out in the two-phase region at state 4, and then we add heat. We add heat from that refrigerated space because the temperature of your refrigerant at that point is lower than the temperature of your refrigerated space. And heat is always going to flow from hotter, the refrigerated space, to colder, the refrigerant circulating throughout this loop here. And then it undergoes an isentropic or an ideally isentropic compression within your compressor. And then it passes through from 2 to 3, it passes through that heat exchanger, the condenser. And because your refrigerant is hotter now, you've compressed it, it's all the way up in that superheated region, and the temperature of your refrigerant is much higher than the temperature of your kitchen, your heat is going to flow from your refrigerant to your kitchen. And then from 3 to 4, you undergo that isenthalpic throttling process all the way back to state 4 and then to state 1, and the cycle, the loop continues. All right. A vapor compression refrigeration or a vapor compression heat pump cycle, it does the same thing. So if you look at your diagram here, you've got all the same components. You've got two heat exchangers, you've got an evaporator and a condenser, you've got a compressor, and you've got an expansion valve. So it's the exact same cycle, it's just you're interested in Q dot H or Q dot out, what's going in to heat your house, as opposed to keeping that refrigerated space cold. Now, that doesn't mean to say that you can't use it as an air conditioner. So your heat pump also probably has a reversing valve, which will reverse the direction of flow of the refrigerant, which would allow you to, instead of heating up the inside of your house, it would allow you to cool down the inside of your house. So in that way, the heat pump is going to actually be running, if that reversing valve reverses the direction of flow, it allows your heat pump to operate on a refrigeration cycle. So instead of having the condenser inside your house, it would be the evaporator inside your house, and vice versa. So, all right. Well, I really hope that was helpful, and thank you very much for watching.